We have Christy on board already. Good deal. Now, can we see all that? I think so. Hello, physics students. Welcome to our 3-hour ordeal tonight. And your exam is Thursday night at 5:30, isn't it? We'll need to talk about that when we get more customers here. Well, we've got Phoebe and Christy. That's pretty good so far. While we're waiting for class, did either one of you guys have a question for me? Just unmute and ask me something if you want. I graded your labs, and I'd like to talk about them briefly. Nobody has any questions for me. We've got Nicholas now too. That's good. Okay, today's the 8th. We're in physics 2, and I wanted to talk about the lab a little bit. You guys had a little trouble with black boxes X and Y. Let me go through those with you, okay? I forget which student it was that had these values. I could go back and look. But with box X, one of you guys or one of your teams, what'd you have, 3 different teams? This is what you guys, your team measured. Now that's what you measured. And here's what I wanted. I wanted the circuit inside the black box, and here's what it is. Let's go through that so that you can be convinced. Let me see how we're doing now. We have, well, it's just the same 3, Phoebe, Christy, and Nicholas. But we are recording. I guess if you had to, you could watch the YouTube video. But if you look at from 1 to 2, you might think you have 3,000 ohms between 1 and 2. But see, you also have this 3,000 and 3,000 in series between 1 and 2. So the actual resistance between terminals 1 and 2, you'd have to do this. Because these two are in series. To get the total resistance between 1 and 2. See, when you measure a resistance, you have to isolate that resistance. You can't have it connected to a lot of other resistors because you're measuring that resistance in addition to the resistance between 1 and 2. Now, if you'll solve this, go ahead with your calculators. I'm going to do it. Go ahead with your calculators and see what you get. I'm doing it right now. And I'll go to one of my wonderful students here. Well, we have Chastity also. Chastity's with us. Good deal. But let me go to my friend Phoebe. Phoebe, do you have that yet? Have you figured out what that is yet?
I just got home. I'm not able to do any of the math right now.
Oh, that's okay. That's fine. Take your time, no problem. Let's go to my friend Christy. Christy, do you have that yet? Earth calling Christy, Earth calling Christy. Come in, Christy. Well, Christy's not answering. Well, how about my friend Chastity? Chastity, did you do this and get the total?
I literally just got in here, so I need to see how it started up.
Oh, that's okay. People are showing up. I'm going to go to my friend Nicholas. Nicholas, he's not going to let me down. Nicholas is he's going to come through for me. Nicholas, do that on your calculator and tell me what you get.
Well, I got the total of 2,000 ohms.
That's what I got. So between 1 and 2, according to all of our knowledge, it should be 2,000 ohms. Well, that's pretty close. What was that, 2,070? It's off a little bit, but that worked out pretty good. So I'm happy. Now let's do between 2 and 3. Now between 2 and 3, it's the same math because you have this 3,000, but you have 6,000 in series with it. So when you solve this, guess what you're supposed to get? You're supposed to get 2,000. Just like my friend Nicholas got. Hey, Zach's with us too. You're with us. Now, if you want the resistance between 1 and 3, it's not 6,000. It looks like it's 6,000 between 1 and 3. But see, you have to isolate your resistor. Let me write that down for you. When you measure resistances, you have to isolate. I don't know if I explained that to you guys. You have to isolate the resistor. What that means is you disconnect it. See, if you wanted to measure just this 3,000 ohms, you'd have to break this. Take this out and just measure the 3,000. But because it's got all these other resistors here, it changes the resistance. So if you want to go between 1 and 3, you notice you've got a 3,000 and you got 6,000 in parallel with it. So it's the same math. And according to our theory, see, this is actual here. This is what one of our teams measured. But according to our theory, you should get 2,000 for each one of them. But you know how it is. These things are never exactly what they say they are. And so you get a little bit of an error there, but maybe not too bad. How much error is it between 2,100 and 2,000? Let me just do that. Hang on. Well, that's 5% error. Difference here between these two is 5%. Well, that's a pretty good resistor if it's 5% within the limits of what it says it is. I think 5% is that gold? Yeah. Yeah, it is. If the fourth stripe is gold, then you're looking at a 5% resistor. And those are the most accurate, aren't they? If the fourth stripe is silver, then you have 10%. It's a 10% accuracy. If you don't have a fourth stripe, then it's 20%. That color code is only good within 20% of what the color code says. Now, when you come and take your test on Thursday, you want to have the color code. Tell you what, bring a 5 and a 8.5 by 11. Bring a sheet of notebook paper and put all your equations you might need on there and the color code, because you're going to need it. I'm going to ask you how to do one of these problems. Let's see how we're doing now. Oh, we've got a good crowd. We got Jacob and Nicholas. And Zach is here. We got a good crowd. I don't know what happened.
On the 8 by 11,
Yeah,
do you want it one-sided or can we do both sides?
it's one-sided, so write small.
Yes, sir.
Write small. Let me write that down for you guys. Now I'm going to erase this. That was box X. I hope you understood it. But a lot of you had trouble with that on your lab. There is no lab on this Thursday night at 5:30. It's an exam. And here's what I would recommend. Bring to the exam. Now it's closed book. On this exam, there's no book. You just use your notes. One page of equations. And I would include the color code for sure. And I would include things like Coulomb's constant and that permittivity constant. Have those written down. Now, if you forget Coulomb's constant and you say, Mr. Griffin, I forgot Coulomb's constant. I didn't put it on my sheet. I'll put it on the blackboard for you, okay? But why don't you make sure you have all that? And your equations have, this test is over 5, 6, and 7. We got to get started on chapter 7. We haven't even gotten started, but we will in a minute. It's on chapters 5, 6, and 7. We'll start on 7. But let me show you one last thing here about your lab. You had trouble with black box Y. And then you can write anything else you want. On one page, write small. You can put a lot of stuff on one page. Okay, now on box Y, most of you had trouble with that. And again, I went to one of your groups and I wrote down what you guys measured. And here's what you measured. And this one was kind of hard to figure out, but let me go ahead and just show you what it was. Okay, now let's see. If you measure between 1 and 2, in a sense, that's isolated because it's not connected to anything. And so you should measure 800. Well, this group got 794. That's pretty close to 800, isn't it? So that seems to work. Now between 2 and 3, you might think, well, gee, there's nothing there, so the resistance would be infinite. No, it's not infinite because 2 and 3 are connected. They're connected around this way. And you know how that works when you have them in series. You have 800 and 800 and 800 in series. They add up in series. So you should measure 2400. That's exactly what that group measured. They measured 2400. That worked pretty good. And then between 1 and 3, you know what you have there? You have the two 800s. You have 1600. This measures almost exactly what the color code said. See, the color code says, color code, this is what you measure. The color code would say 800, but it'd say 2400 and 1600. So that's what you got on that. So I hope that helps you. And if you have something like that on your test, maybe you'll be okay. We hope. And you've learned that if you want to measure resistance, you have to isolate the resistor. Okay, any comments or questions on any of that? Yeah, all right. Say goodbye to box X and box Y.
Do we need those resistance equations on the test?
Absolutely. Yeah. You don't need me to write them, do you? Well, I wrote that one in series.
Sure.
You know how it goes. This would be the total Now that's in series. See that other one I had, that's in parallel. But yeah, you want to have that on your test, sure. Absolutely. Okay, now let's talk about chapter 7. Chapter 7. Now the name of the chapter is electric potential. I believe if you dig into your book here, I believe that's the title of the chapter. Yeah, that's it, electric potential. And that's a fancy name for voltage. And we're going to learn what voltage is here in a minute. And I know you've heard about voltage. If you have a lamp and you plug it in, it's a 110. It's 110 volts, isn't it? AC. And what voltage is it's energy per charge. That's what it is. In fact, it's joules per coulomb. So now you know what a volt is. A volt is a joule. I really shouldn't capitalize those. Should be lowercase. A volt is a joule per coulomb. Now I always put my units in brackets. There we go. Or you could just say a volt is a joule per coulomb. Later we're going to learn that a volt can also be expressed as a just a minute now, I'm having a senior moment here. No. What I was going to say to you is that you know that electric fields are newtons per coulomb. You know that, don't you? Electric fields are given in newtons per coulomb, but they can also be given in volts per meter. A newton per coulomb is equal to a volt per meter. Let's see if we can show you why. Now you know what a volt is. It's a joule per coulomb. So you have a joule.
What does it say after voltage, right, in the upper right-hand corner?
Oh, thank you. This says energy per charge, and this says joules per coulomb.
Thank you.
Yeah, thank you. Okay, now I was going to show you that a newton per coulomb is the unit for electric field, and it should equal a volt per meter. Let's see if I can show you that. Well, see, a volt is a joule per coulomb, and we've got a meter down here. That didn't come out to be a newton per coulomb yet, but I haven't given up yet, because we know what a joule is. A joule is a newton times a meter. A joule is a newton times a meter. So if you put that in there, newton times a meter, and divide by a coulomb times a meter, ooh, the meters cancel. And can you see that you got newtons per coulomb, newtons per coulomb. Electric field can be expressed in newtons per coulomb, which we already know, or volts per meter. Interesting. So we had a little review there of some basics. We all knew that a joule was a Newton meter, I hope. Okay. Any questions on that? All right. If you're happy. The name of this chapter is electric potential. They could have named it voltage because that means the same thing. Electric potential equals voltage. It's the same thing. Now there's something else that's different though, and that's called electric potential energy. Electric potential is one thing. That's in volts. But electric potential energy is not in volts, it's in joules. It's potential energy. There are different types of potential energy. There is gravitational potential energy. I would like to talk about gravitational potential energy for just a minute. It's in joules. I think maybe you understand what that is. I bet you've studied that. Gravitational potential energy. You know what it is? It's MGH. The way I always wrote it was potential energy like this. But your book writes potential energy like this. It's a capital U. P dot E dot better, because I know exactly what that is. It's potential energy. But never mind, your book, I think, likes the symbol U for energy, and so we have to live with that. Have you ever seen this? Potential energy, gravitational potential energy. It might have a little h, I don't know which school you went to. Let me ask one of my students. How about my friend Zach? Zach, have you ever heard of MGH, Zach?
Yeah.
Yeah, he's heard of it. MGH. Absolutely. Well, let's see if we can do an example of that. I don't have a here, but here I am, and okay. Not very good. Not very good artwork there. But see, if you have a rock right here, it's a let's suppose it's a 2-pound rock, and suppose this is 2 feet. Well, you got mg is the weight, and so you have 2 pounds times 2 feet. You know what? You got 4 foot-pounds of energy there. If you take a 2-pound rock, that's slightly smaller than a kilogram, because a kilogram's 2.2 pounds. Kilogram's a pretty heavy chunk of metal, you know it? And you put it over your head 2 feet and you drop it, probably knock you out. Even break your skull. I don't know. Pretty stupid thing to do. It's got 4 foot-pounds of energy. The units in the English system are foot-pounds for energy. Here, let's do it in the metric. If you had 1 kilogram, and say this is 1 meter, then what you have is MGH. You have 9.81 newtons times 1 meter. See the weight is equal to mg, and g is 9.81. If you got 1 kilogram, 9.81 times 1, you got 9.81 joules. So that amount of energy is going to hurt, okay? But now if you drop that rock from a shorter distance, like maybe, let's drop it from, I don't know, 2 centimeters. There you go. We're going to drop, it's going to be much less energy. It'll be 9.81. It still has the same weight, but this is only 0.02 meters. And the amount of potential energy that you have is 9.81 times 0.02. I'm only getting 0.1962 joules. It's just a fraction. I think I could handle that. You could drop that kilogram from 2 centimeters. I don't think that'd hurt that much. That's gravitational potential energy. And see, the higher up it is, the dangerous it is, because it's got more energy. That makes sense. Well, if you understand that, let me give you the 2 most important equations in this chapter. I need some room here. Let me say goodbye to all this for a minute. The 2 most important equations, I think, in the chapter, let me see if I can find where they are here. Here's one. It's on page 292. It says, talk about that in a minute. You know what? They don't have the other important equation. They have that one, and they have some other important equations, but they don't have this one here. But this one here is called the work energy theorem, and it goes like this. Have you ever heard of the work energy theorem? Yeah, the work. Let me ask one of you guys. I bet you have. Well, you took physics 1. Jacob,
Yes, sir.
you took physics 1, didn't you, Jacob?
Yes, sir.
And
We did go over.
Jacob, did they ever tell you about the work energy theorem in physics 1?
Yes, sir. We covered it.
Absolutely. It's terribly important. Like, for instance, back to this rock. We'll talk about this in a minute. Back to this rock. If you dropped it, how far was it? Was it 1 meter? Was it? Yeah, I think we have 1 meter and 1 kilogram. And if you drop that rock on my head, You'd have to be pretty mad at me to do that. Okay. Well, we already figured it out, the energy it has. And so if you come up here, the change in energy of that rock is negative. See, it has a 9.81 joules of energy here, but when it gets down to my head, it loses that potential energy. And so the change in potential energy is negative. You're losing. When you drop a rock, it has more energy when it's up high, and then as it falls, it loses its potential energy. So the work done is equal to the negative of the, wait a minute, I need another negative here, guys. Negative, this equation's on page 292. Now the change in energy as that rock falls is a negative 9.81 joules. And you got two negatives, so you got 9.81 joules is the work done by gravity. The gravity is doing work, and that work is equal to the change in kinetic energy of the rock when it hits my head. I'll tell you how fast it's going. We know what the work done is. It's 9.81 joules. And kinetic energy is 1/2 times the mass times the velocity squared. So get your calculator, and we can figure out how fast that rock is going if you drop it from 1 meter. Go ahead. I'm getting that rock, hits my head going 4.429 meters a second. That's the work energy theorem. But now this is not the work energy theorem. You know what that is? That's the definition of potential energy. This chapter is about potential energy. It's about potential, which is voltage, and potential energy. Now, potential and potential energy are different. They are different. Let's review what they are. Potential another name for that is voltage. The full name is electric potential. And what that is energy per, it's energy per charge. No, it's just energy. No, it's energy per charge. There we go. I was getting myself mixed up there. And electric potential is energy per charge, but electric potential energy is different. You don't want to get them mixed up. This is just energy. It's not energy per charge. It's just energy. See, this one here is in volts. This one's in joules. This equation here, that's supposed to be 3 lines there. That's a definition. What this says is the work done by your electric field is equal to the negative of the change in your energy. And that equation is on page 292. You'll see it. It's on 292. Well, those are the two big important equations in our chapter. The definition of potential energy and the work energy theorem. Any comments or questions so far? Okay. Let's work a problem. Let's work this example 7.1. Here we go. You can easily get mixed up here. You know that? Electric potential energy and electric potential. They're different. Get mixed up if we can help it. Well, let's see if we can do a problem here. This is example 7.1. I'd like to do some problems in your chapter too. The back of the book there, or in the back of the chapter. But what they've got in this example 7.1, they have a 5 nanocoulomb, and then 10 centimeters away, they have a 3 nanocoulomb. And then what are they going to do? Well, you know what's going to happen. Now this one, they don't let it move. What they've done is they've stuck it to some, put some super glue there and put it on a table. It can't move. But this one is free to move, and you know what it's going to do? It's going to take off. It's going to take off, and it's going to go 5 centimeters, they said. Okay. So that'd be about here maybe. See, after a little bit, it's going to be here. The 3 nanocoulombs. And you know what? It's going to have a velocity. It's going to have some speed. We're going to have to use that work energy. You know what? If we could figure out the work done by the electric field, it's equal to the change in kinetic energy. Okay? We could get that if we could only figure out the work done. All right. Now, do you remember how to do work? That W stands for work. Yeah, go ahead.
I was just asking if you could write a little bigger. It's hard to see today.
Thank you. I'm going to write bigger. Hey, how's this? Bigger, isn't it?
Yeah, that helps a lot.
Yeah, we'll do that. Thank you so much. Now, you know what work is? It's force times distance. Force times distance. If you knew the force, I don't know, 3 newtons maybe, and you knew the distance, say 2 meters, you know what you'd have? You'd have 6 joules. You'd have 6 joules. That is if the force and the distance are going the same direction. If they're going the same direction, you'd have 6. You'd have a positive 6. But you know what? If you had a force of 3 newtons, but the distance was going this way, 2 meters, you know what? You'd have a negative 6 joules. See, work is really a dot product. Work is force dotted with distance. You can make a vector out of it. Do you remember dot products go F, D, cosine of theta? Now, if they're both going the same direction, cosine of that theta is just 0. Cosine of 0 is 1. But if they're going in opposite directions, you got a cosine of 180. Cosine of 180 is -1. So you get negative work. And here's the problem with this example 7.1. The force is changing. Now let me show you what it is right here. Right here, we can figure that force. It's from Coulomb's law. You know how to do Coulomb's law. Let me make a little room here. We're going to do Coulomb's law. That force there will be K, 5 nanocoulombs, 3 nanocoulombs. In the problem, if you'll read it, it's 10 centimeters, so it's 0.10 meters. So you got to go 0.10 meters squared. Okay. We're going to do that. Put that'll give us our force. Do that with me. Let's see if we can get the same thing. Go for it.
You wrote small again. I can't see your distances.
Keep after me. Do not let me get away with that. All right, put that in there. Remember what nano is. Okay, I got an answer. Let's go to one of my students and see what they got. Phoebe, do you have this yet?
No, I'm still working on putting it into my calculator.
Take your time. What about my friend Jacob? Do you have this yet? I have an answer. I don't know if it's. Go ahead.
Is it like a 13.4 or something?
Yeah, that's it. Yeah. Well, actually, what I have is 1.34 something. Jacob, is this what you have?
13.485, yes.
Yeah, but what is your exponent?
I just got a flat. I must have left something off.
Ah. Now, nano is 10 to the minus 9. Nano is 10 to the minus 9. K is 8.99 times 10 to the 9th. Do it again, Jacob. And tell me if you
Yep,
get this.
I got it right.
Got it? Now, you
I got
know
it.
what? We could write that, like Jacob says, as 13 micronewtons. See, what I did is I made this smaller, -6, and made that bigger. So what we got here is 13. I don't want to write small. One of my excellent students wants me to write bigger. So we got 13 micronewtons there. But see, when it gets to here, you're going to discover the force is smaller. Here, let me draw that. I'll put a little red arrow here, but this little red arrow is smaller. See, here's the force here, but the force here is smaller. Now let's get that.
I'm getting like 8.
Let me do mine again. I'm going to go 8.99 e to the 9th times 5 e to the minus 9
Oh, that's a
times
5.
3.
Okay.
You okay?
Yeah, I have 2 3s instead of a 5, so that's what
Okay. I need to write bigger is my problem. I need to write bigger. Okay, we're going to find what this force is here. Now, this force here is smaller. It'll be K 5 nanocoulomb, 3 nanocoulomb. But see, this is 0.15 meters. Do that. See what you get.
5.993 repeating e to the -6.
Man, you're faster than I am. But yeah, that's what I got. Why don't we just write it as 6 micronewtons? Isn't that what that is? It's 6 micronewtons, isn't it? Look here, you had 13 micronewtons. Here you got 6 micronewtons. Now you went a distance of 5 meters. So how do you figure the work done? There's some room here. See, work is force times distance. But see, the force is changing. Hey, they invented calculus for things like that, didn't they? They invented calculus because it's changing. So what you do is you go and you integrate the force over the distance, like that. You take the integral, because it's changing. That's why they invented calculus, because some things change on you. It's not a constant. Force changes. Okay.
So is
Go ahead.
Is micro to the -6 or to the -9th?
Micro is -6. I'm getting 6 e to the -6. How about you?
I was just asking when we entered the
For this one, when you do this one, what you get is 6 micronewtons. When you do this one, you get 13 micronewtons. You okay?
Yep.
Now, who was that?
Jacob.
Jacob. Thank you, Jacob. Now what we're going to have to do is we're going to have to integrate this. Because which force do you use? Well, you don't use either one of them. You integrate it. All right, well, let's do that. I'm going to make a, here we go. I need some room here. We're going to integrate. And they do this in the book. You guys could read the book if you had to. But the work done to get from here to here is the integral from 10, and I need to write a little bigger, from 10 to 15 of the force, which is K times 5 nanocoulombs times 3 nanocoulombs over R squared dr. But we have to integrate that because it's changing as R changes. Okay, but we have a bunch of constants in the numerator. Now, when you guys took calculus, I know they taught you this. They taught you, can you read my writing? That's an x squared in the denominator. They taught you that that's equal to -1 over x, didn't they, calculus students? Isn't that right? Somebody say,
Yes.
oh, yeah, that's right. So you see
Yes.
what, go ahead.
Oh, I just said yes.
Oh, good for you. Good for you. So when you do this, you know what you'll have? You can pull out all these constants. and you'll have a minus 1 over R, but you have to put in the limits. Because we're going from 10 to 15 centimeters. So let's see if we can do that. I think we can. So I'm going to do this on my calculator, and I want you to do it. Can you read that? I bet you can. Here, I'll write it out a little more for you. You got K, 5 nanocoulombs, 3 nanocoulombs. And we're going to go negative 1 over 0.15 minus a negative 1 over 0.10. That's what we're going to do. Because you have to put in the limits. Okay, do that. Tell me what you get. Well, I got an answer, and it's the work done by the electric field and I got 4.495 10 to the minus 7 joules. Well, what did they get? Well, they got the same thing. Look, I'm on page 291 right now. And you know what? They got the same thing. You had to integrate because of the force changes, but we knew how to integrate that. And that's the work done by the electric field. That's all the work that's done on it. There isn't any other work. And so therefore, if you add up all the work and that's it, you get the change in kinetic energy. See, it started with 0 kinetic energy, and now it has 4.495. You can make that fancy-wancy if you wanted. If you make this 10 to the minus 6, that makes it bigger. You'd have to make that smaller. So it's 0.4495 microjoules of kinetic energy. Does that make sense? And read what they said there. They said that that answer that we got is also the value of the kinetic energy. Okay, great. Now, voltage is energy per charge. If you wanted the voltage here and here, we could get it. You just say this is your test charge, divide that 3 nanocoulombs into the 13 micronewtons, and you could get your voltage there, and you could get your voltage here. Okay. Well, why don't we do that? That'd be fun. But did you understand what we did so far? We just did that example on page 291. Hey, we got what they got. We did good. What about that equation? The work equals the change of it's equal to the negative of the change of your potential energy. Well, we got the work done. It's this here, and it's positive. this work done is 4 point, here we can round it off, 4.5 or better yet, 0.45 microjoules. So what's the change in potential energy? Well, it's negative. You lost some potential energy. Did you know there's more energy here than there is here? Now you gained kinetic energy because you started off at rest and you sped up. You speed it up. What's correct? You sped up, you speeded up. I don't know. We'll have to take English sometime. Go ahead. Sped up?
Yep.
Yay, good. I learned something. Okay. Now, what was I going to say? I had a senior moment there. Oh, we lost some potential energy, but we gained some kinetic energy because it's sped up. Yeah. This situation is a little bit, let's see if I can explain this. It's a little bit like a compression spring. Here, let me draw you that. You know, you guys know that you have shocks in your car.
Yes, sir.
Oh yeah, you got shocks. And they have different kinds of shocks. Some of them, especially on trucks, are springs like that. Now,
Leaf spring.
yeah, well, they have leaf springs and they have the coil springs, and some trucks have what do they call that? A shock absorber inside the spring. Of course, they have to have connections here like that. But as you compress this thing, here we just compressed it, and the shock absorber is compressed too. There's more energy. There's energy in that. It's like this. See, when you take these two pluses and you put them together, here they are here. You got these two pluses. They don't want you to put them together. Look, here's these two pluses, and you've forced them to go together. There's more energy here when they're like that. But see, when they're like this, of course, I'm exaggerating like crazy here. There's less energy on a compression spring, that is. If it's a tension spring, it's a little different. I don't know if that helps you, but well, it's kind of like a rubber band. If you have a rubber band, here's a rubber band, and you stretch it, guess what? There's more energy in that rubber band when you stretch it, isn't there? But the analogy here is it's like if you had a positive and a negative charge, and if you stretch them apart, there's more energy there. If they're both positive and you stretch them apart, there's less energy. Think about that for a while. Now, to understand the energy in a rubber band, take the rubber band and bite it with your teeth, pull it about as far as you can go, and then let go and snap it. Pop! It hurts your lips, doesn't it? It's a stupid thing to do. But see, there's energy stored up in that rubber band. There's energy stored up when you push these positive charges together, or when you pull opposite charges apart. Okay, well, that was fun. All right, well, let's move on here. We did an example. Let's do another example. I need some room here. We're going to do example 7.3 now. Okay. This is example 7.3. And what they've got is, well, it's a square. They have a square. There we go. Trying to draw a square here. That looks pretty good. We're trying to draw a square. Yeah, that's halfway decent. Now they're going to put a 5 microcoulomb charge here and a 4 microcoulomb charge here. These are all positive. A 3 microcoulomb, come on now, 3 microcoulomb and 2 microcoulomb. They're all positive. Those are 4. Did I write that big enough where you can read it? It's supposed to be a 3 microcoulomb down there. This is supposed to be 4 microcoulombs. I hope you can read my writing. They're all positive. They don't want to go like that close. They'd like to get the heck out of Dodge. They want to go away. They don't want you putting them that close. And so there's energy stored up here. We've shoved those charges together like that, and we've accumulated some energy. We're going to find out how much energy, but we're going to do it one charge at a time. Let's start with maybe the 2. Let's have our square here, and these charges here, they're going to be out here at infinity someplace. Far, far away, you've got a 5 microcoulomb, a 3 microcoulomb, and a 4 microcoulomb. They're way out here miles away. Well, you had a 2 microcoulomb also. And see, it wasn't there to start with. And what we're going to do, they're all positive. We're going to take that 2 microcoulomb and put it right here. Here he is. There's your plus 2 microcoulombs. But see, that didn't require any work. Remember how it works? The work is equal to the change in, well, it's equal to the negative of the change. Here's the equation that we're trying to teach you. It's actually a definition. It says that the change in your potential energy is equal to the negative of the work done by your electric field. Well, there is no electric field. There's nobody around. You could bring that 2 microcoulombs in and stick it right there. It didn't require any work at all because there was no opposition. We got rid of the 2 microcoulombs. Now let's put let's take the 3 microcoulombs. Here we go. We're going to bring it in and we're going to put it right here. Now he doesn't want to go there. See, he's being repelled. You're going to have to do some work to get him in there. Now the amount of that work, we just did an equation like that. The amount of that work to get him in there is K, 2 microcoulombs, 3 microcoulombs. Remember after we integrated, It wasn't R squared, it was R, and the R was, they said it's 1 centimeter, so it's 0.01 meters. And now, is this work positive or negative? Now, let me think now. Your force is repelling and you're moving this way. See, the force is this way, but your motion, your distance is this way. You know what? That's a negative, isn't it? The amount of work done by the field is negative because the force is trying to push you away and you're moving them in. See, this is the work done by your field. It's not the work done by Griffin that's bringing this charge in or some other external force. It's the work done by the field. And the work done by the field is negative. Okay. And when we integrated on that other problem, it was -1 over R. You don't have it squared anymore. I think we're done. Ah, but that's a negative. The work is negative, but see, this is it's got a negative. You got two negatives. So the amount of energy that you have, we'll say that the amount of energy out here is 0 to start with, but the change in energy that you have right now is this. Only it's plus because you got two negatives. So right at the moment, here, I'll write it down here, there's room. We're going to get the total energy. Right now, with these two charges, our total energy is equal to a positive 2 microcoulombs, 3 microcoulombs, 0.01 meters. Okay, we're ready to bring in another charge. Let's bring in the 4 microcoulombs. See this 4 microcoulombs? We're going to bring it in. Now it does not want to go in here. You see these positive charges? It's repelling. The field is doing negative work. Now I'm doing positive work because I'm shoving it this way and it's going that way. But we're going to shove it in right here, and there's your 4 microcoulombs. But now here's the energy. The energy is going to be K, 4 microcoulombs, 3 microcoulombs, 0.01 meter. But you've also got energy because of this guy. So that's going to be K, 4 microcoulombs, 2 microcoulombs. But see this distance here, if this is 0.01 meters, this is 0.01414 meters. Pythagoras tells us that. So you got to divide by 0.01414 meters. Well, we got that brought in, and let's see, we brought in the 2, we brought in the 3. We only have one more to go. And we're going to add these up. Each time you bring one of these in, you're increasing the energy. Okay, well, we've got to bring in this 5 microcoulombs. So here goes. And it's going to go right up here. We're going to bring it in. Here it comes. It does not want to go there. See all those pluses? These are all pluses. But we're going to bring it in and we're going to stick it right there. And here's the energy for that. It's going to be K, 5 microcoulombs times 4 microcoulombs, 0.01 meter. That's the energy to bring it in here. Here's your 5 microcoulombs. But see, you're also got some energy because of the 5 and the 3. So it's K, 5 microcoulombs, 3 microcoulombs, 0.01414. Need a little room here. And don't forget, you still have the 5 and the 2. So you got K, 5 microcoulombs, 2 microcoulombs, 0.01 meter. You're going to have to add up all 6 of these. There's 6 terms here. See them? If you add up all 6 of those, you'll get the total energy to build this square with these charges. Now what I'm going to do is I'm going to pull out, I'm doing a little algebra here. I'm going to pull out the K and the micros, and I'm going to go like this. I'm going to pull out the K. Here, let me make a little room here. There's 6 terms here, and we're going to get the total electric potential energy of this configuration. Here we go. I'm going to pull out the K, and I'm going to pull out the micro and the micro. That'd be 10 to the minus 12, you know it? And then what I'm going to do is I'm going to add up all 6. If you start with this, what you'll have is 6 divided by 0.01. This will be 12 divided by 0.01. Doing a little algebra here now. This will be 8 divided by 0.01414. And don't forget these terms. This will be 20 divided by 0.01. This will be 15 divided by 0.01414. And this will be 10 divided by 0.01. Now, get your calculators, plug these 6 things in there, multiply them by K times 10 to the minus 12, and tell me what you get. I'll shut up for a minute. Go for it. Don't peek in your book, because they do this in your book. It's on page 295.
Following you, but it wasn't the same.
Say that again.
What did you add to get those top numbers? I thought I was following you, but it wasn't the same.
Oh,
This
2 times 3 is 6. 4 times 3 is 12. 4 times 2 is 8. There's a 6, 12, and 8. 5
okay,
times,
you're adding them. I see.
yeah, 5 times 4 is 20. 5 times 3 is 15. 5 times 2 is 10. Go for it. I'm going to do it too and see what I get here.
And you divide it by 0.01414.
Yeah, this one's 0.01414, and this one is too. See, that's those distances here, 0.01414. Well, believe it or not, I got an answer after plugging all that jazz in. I got 57.77 something, and it would be joules, wouldn't it? We're doing energy, right? I wonder if that's right. Let's see what the book got. boy, Joe, the book got 57.8 joules. Hey, we did great. But I'm going to wait till I hear a couple of uh-huhs from the crowd there. I don't hear any uh-huhs. What we're doing is we're plugging all this in here. And don't forget, you have to multiply by K and by 10 to the minus 12. And I got 57. And I'm waiting for an uh-huh.
I got 5.77 times 10 to the negative 8. Were you doing K and 10? Oh, I think I mixed this. I mixed a couple together.
There's 2 microbes. See, that'll make a 10 to the minus 6 and a 10 to the minus 6. That's a 10 to the minus 12. And you know what K is? That's 8.99 times 10 to the plus 9. I think you did it right, but you got an exponent problem. Is anybody?
Yeah, I got it.
Yay! Yay, good deal. All
All
right, excellent.
K threw me off.
Now let's get down to the kind of thing that might help you on your test, because we're supposed to have something about this chapter on your test. See, that's potential energy. Now we're going to talk about potential. They're different. I need to make some room here. I'm going to make some room.
Was the answer in joules?
Yes. It was 57.77 joules is what I got. Now the book, if you look at the book, they got 57.8 joules on page 296. So we got what the book got. That's good. Now we've talked about how to get the change in potential energy. But what voltage is, if you wanted the change in voltage, it's just the change in potential energy divided by your charge. See, voltage is energy per charge. See what a volt is? It's a joule per coulomb. Now, if you have a constant electric field, it's pretty easy to find the change in voltage. It's just equal to your electric field times your distance that you move in that electric field, if you have a constant electric field. Now the reason for that is, see, the electric field is, you know what that is? That's force per charge. And if you multiply by distance, if it's a constant, if the force is constant, that's the work done. And so you get the work done per charge. And the work done per charge is equal to the voltage, the change in your voltage. Remember, here's how it works. The change in your potential energy is equal to the negative of the work done by the electric field. And so you can get the change in your voltage. If the work done is force times distance, and if you want the force is equal to the electric field times charge, and see if you divide that by charge, you just get your electric field. You know what the electric field is, it's force per charge. I don't think I'm explaining this very good. The way I taught one class was I had a guy named Ed in the class, and I said, now Ed, your job is to remember, if you have a constant electric field, that your change in voltage is just your electric field times the distance. Can you do that for me, Ed? And he said, well, sure, Mr. Griffin, no problem. Here, let me give you an example.
So it's the electric field times distance, is what you're saying?
If the electric field is constant, and see that's what you have with a sheet of charge or a disk, a big enough disk, you get a constant electric field. And if you take a charge and you move it from here to here, at distance d, then the change in voltage is equal to the electric field times your distance. Now, it's going to be negative because a positive charge going downriver like this is losing energy. And so you have less energy, but the amount is ED. The amount is ED. Like for instance, suppose you had a sheet of charge, a great big sheet of charge. Okay, here we go. Big sheet of charge. You know that the electric field on a sheet of charge is equal to sigma over 2 epsilon 0. Well, see, that's a constant. That's a constant. And if you had a positive charge and you put it there, you know what it's going to do? It's going to take off. It's going to take off. And the change in voltage of that charge will be equal to E times D. Okay, that's energy per charge, change in voltage. All right, well, and it'll speed up too, you know what? See, that's the energy per charge. If you wanted the energy by itself, the energy would equal the charge times the change in voltage. So that would equal your kinetic energy. So if you knew the mass of the charge and you knew the electric field, you could get the change in voltage if you knew the distance. Yeah, I think you could find the kinetic energy. We could do a problem like that. So this is a nice equation if you have a constant electric field, but not all electric fields are constant. Let's do one where it's changing on you. See, these are constants. That sigma is a constant for a sheet of charge like that. You know what that sigma means, don't you? It means the charge density. I don't want to answer that. I can't answer that. We probably should work a problem like that. Let's see if we can. I think there's one like that in here. We need to take a break here in a minute, but I think we got time to work one problem like that. Let's see, here we go. I bet we can do this. Up again. We need to take a break. You're probably getting tired of listening to me. I wouldn't be surprised. Yeah, totally organized as always. And I'm gonna have to get the air conditioning going again. It's starting to get hot. A hot day. Yeah, now this looks pretty good. This is 739. I bet we can do this. This is problem 739. We're going to do this. We'll take a little break, and then we'll do one where the electric field changes on it. Now, if you'll read this problem with me, help me find it. Where is 739? Trying to find it here. Okay, I finally found it. Two parallel conducting plates are separated by 10 centimeters. We're doing 739, and here they are. Here's these conducting plates. They're separated by 10 centimeters. All right. There's 10 centimeters between the plates. Yeah, that looks pretty good. One of them is taken to be 0 volts. Let's say this one is at the 0 volts. In electronics, they have a little symbol called the ground. It's kind of arbitrary. It just means that they're going to call that the 0 voltage there, the ground. Okay. What is electric field strength? Well, let's do that. Now, if this is positive, we're going to charge this up positive, okay? And you know there's going to be an electric field in here. And that electric field is equal to, we've done this before. For two uniformly charged plates like that, that's the equation. Now, do they tell you how much charge it is? Well, I don't know. We're doing problem 739. I'm on page 341. They tell you how much charge? Let's see. 10 centimeters. 8 centimeters from the 0 volt plate and 2 centimeters from the other is 450 volts. Okay. Well, see, you're 8 centimeters from the 0 volt, so you're located right about here. This distance is 8 centimeters. And that little bitty distance there is 2 centimeters. And they said the voltage here, right there, the voltage is 450 volts. I don't think we're ever going to get this. They didn't give us the charge density. So that's a nice equation, but never mind it right now. We don't know what the charge density is. But we do know what that voltage is right there. And if we only had Ed in our class, he could tell us that if you have constant electric field, and you do, because remember the electric field is just sigma over epsilon 0. Those are both constants. So it's constant. And the change in voltage from here to here, if this is 0 here, we'll put a delta there. Well, what that means is the voltage here minus the voltage here, which we'll call 0, so I don't really need a delta, is equal to E times D. Now the D is 8 centimeters. And they gave us the voltage, it's 450. So we have 450 volts. Pretty easy to do when you have constant electric field. Now help me do that and find the electric field. Find the electric field inside these plates. Go for it. Well, I got an electric field. Let's go to one of my wonderful students here. Let's go to my friend Nicholas. Nicholas, unmute and tell me what you got for the electric field inside here. Inside these charts. Yeah.
36 something.
Well, what I got, take 450 and divide by 0.08 and tell me what you get. I don't think you get 36. Here's an equation.
5,625.
That's better. Now, what will be the units on that? Now, I think I'm talking to Nicholas, aren't I, Nicholas?
Yep, that's right.
What's the units?
I have no idea.
Well, no.
Volt meters or
Meters,
volts
yeah.
per meter?
Yeah, you could say that. It's newtons per coulomb because it's electric field. Or you could say volts per meter. That's okay too. They're the same thing. Remember I was telling you earlier. Okay, great. Well, we got that. Let's see how we did. This was problem 739. Go to the back and help me look that up and we'll see if we got that right. 739, they said, 739, they said 5.63. Here's what they said. 5.63 kilovolts per meter. You know what? I think that's the same thing we got. Look at that. They just wrote it different. We're okay. That makes sense.
Yes,
Now,
sir.
they wanted something else. Let's see what else they wanted here. Go ahead. I'm listening.
I was just saying yes because you asked if it made sense.
Oh, yeah. Thank you. Thank you very much. Now, if the potential 8 centimeters from the 0 is, we did that. Part B, what is the voltage between the plates? Well, now what they want is, what's the voltage between the plates? See what we just cooked up for them is the voltage between here and here. It's 450 volts there, but now they want the voltage between the plates the whole way. Well, how would you do that? I tell you what, we're going to go back to our friend Ed. If you know the electric field, and we do, we figured it out, and you know the distance, boy, Jove, you can figure out the change in voltage. Okay, let's do that. Here goes. The electric field is 5625 newtons per coulomb. And this total distance, they want the total change in volts between these two plates. That's 0.10 meters. Hey, I can do that in my head. I can do that in my head. I'm getting 562.5. See, a Newton meter is a joule. And so you have a joule per coulomb. And that's what a volt is. Remember, a volt is a joule per coulomb. Now let's see how we did. Go to the answer book. We just did 739, and they said the voltage between A and B is 563 volts. They rounded up. The book says 563 volts. Yay! We did good on that. Now we're going to take a 5-minute break. Go get a drink of water. Go ahead.
Why'd you end up using 0.01?
0.01. Where I use a 0.10. I didn't use a 0.01, did I?
Okay, so where did that come from though?
Oh, well, they told us we had 10 centimeters between these plates.
Right.
And that's equal to 0.10 meters,
Oh,
right? That's where I got the 0.10.
and then the 0.8 came from the other given part in the problem.
It's in the problem. They said that 8 centimeters from the right-hand plate, the voltage was 450. But see, the voltage across the whole thing is bigger. It's 562.
Okay.
Okay, we're going to take a 5-minute break. Go get a drink of water or something. We're going to come back, and we're going to talk about the voltage when the electric field is not constant. See, that's a constant electric field. We're going to do one when it's not constant. So go take a break. We'll be back. We will be back. Well, I got lucky. I went downstairs and there was pizza down there. So I had half a piece of pizza. That worked out good. It was that kind Tombstone, you know, where you buy a frozen pizza, put it in the oven, you got yourself a pizza. Not bad. Okay, I wonder if we have, let's see if we still have somebody. Yeah, we still got some dedicated students here that are still with us. Good deal.
Still here, sir.
Yeah, you're still here. Now we're going to talk about the voltage. Remember what voltage is. It's see, that's kind of a blue color, but I guess that's all right. Voltage is energy per charge. There we go. Voltage is energy per charge. Now, if you have a point charge like this, a positive charge, the electric field is pretty big close to it, like that. It's pretty big. You all know how that goes. But see, as you get further away from it, you know that the electric field gets smaller, doesn't it? Yeah. Down here, the electric field is smaller. And then when you get far, far away, the electric field is tiny. It's just real teeny tiny. Now, what about energy? Well, you've got more energy here than here. It's kind of like a river. Get your canoe in the river, and the river will take you downstream. It's kind of like dropping a rock. You drop a rock, and it falls. You got less energy when it hits the ground. The energy is all gone when it hits the ground. See, the river will push that canoe down the river. Now, whenever you're talking about potential energy, they have a reference level. Now, like for gravity, the reference level is the ground. You say you have zero gravitational potential energy at the ground because you know the equation, it goes, the potential energy is mgh. Well, if the h is 0, you don't have any. This is called the reference level. The reference level for gravitational potential energy is the ground. That makes sense. And then the higher up you go, the more gravitational energy you have. See? Now with a charge like this, a point charge, see, they call that a point charge. That's the name of it. The reference level is at infinity. You go out here to infinity, and the potential energy, only the book uses this U. They like this U symbol. They say that the potential energy is 0. out there at infinity. And then as you move in here closer with your test charge, you always use a positive test charge. It doesn't want to go in here because you're increasing the energy. And if voltage is energy per charge, you're increasing the voltage. And what we need is the equation for voltage of a point charge. Well, the equation goes like this. It kind of looks like some of the equations we've had before. It's KQ over R. I'd like to show you where that comes from, and then we'll work a couple of problems. Let's see if I can find that equation there. You're going to need that equation Thursday night, so I'd like us to understand it. There it is. I see it on page 3. I see it on page 311, but it's probably a bunch of other places. Let me look around here. There it is. It's on page 309. Page 309. This is the equation for a point charge. Now, how did they get that? Well, you could read how they got it. It's right here in the book someplace. Let's see if I can find it. I don't see it. Maybe you can find it for me. There it is. It's on page 303. They show you how they got it. You can read that. It wouldn't hurt you any. Page 303. Well, let's see if we could go through it. We'll try. We're going to go. We're going to go from an infinity to some distance r. All right, that's the big plan. We're going to do some calculus now. You guys love calculus. And we're going to come up with this lovely equation, then we're going to work a couple of problems, and then I guess we'll run out of time. Okay. You know that the change in voltage, we're going to go from infinity all the way to some distance r. How about we call this r? This could be point P. There you go. And we're going to start out here and we're going to go to point P. And you know that the change in voltage is equal to the change in potential energy. They use a U. I like PE, but we'll do what they said. And you divide by your test charge. We'll take a test charge out here. It's always positive, and we'll move it in. Now, it doesn't want to go that way. You're going to have to push. And didn't we learn that this is equal to the negative of the work done by the electric field? By definition. Really, it's by definition. And remember, we learned what work is. Work, there's a negative there. Work is the integral of force times distance. It's really a dot product. And we're dividing by Q. You could put that Q inside the integral. It's just a constant. And you know what you'll have? You'll have the integral of E. There's a negative sign out in front. E ds, dot ds. Okay. So far, so good. Now the ds is going this way. And the electric field's going this way. You know what? There's 180 degrees between that electric field and the ds as you're traveling along. So some books have a dl. It's just the distance that you travel. So I'm coming along here. We're going to find the voltage going from infinity to some distance r. And where we're at right now is negative E ds cosine of 180. Well, what's the cosine of 180? Let's go to one of my excellent students here. Zach, what's the cosine of 180? Unmute. I haven't lost you, have I, Zach?
No, but you did cut out. I don't know what you asked.
Well, yeah, what's the cosine of 180? I know you know this. Hey, if you don't know it, just put it in your calculator. Put in 180 and hit cosine and tell me what happens.
-1.
Say that again, please.
-1.
Yeah, but it's -1, isn't it, Zach?
Yeah, -1.
-1, yeah, good going. All right, great. Okay, well then, that's a -1, and we have a negative here. Two negatives go bye-bye. And you have EDS. I haven't lost anybody, have I? Uh-oh.
Where did E to the come from? I mean, where did the cosine of 180 come from?
Oh, thank you. Whenever you're taking a dot product of two vectors, thank you for asking. Did you know that it's equal to the magnitude of the vectors multiplied times the cosine of the angle between the vectors? This is what a dot product is. I know you've seen dot products before. They have dot products. Look in your chapter. I see them. I see a dot product on page 303. It's a dot product. I see a dot product on page 305. I bet they're all over the place. I see one on 308. It's a dot product. I bet there's more. I can't find them right now, but that's what that dot product is. Okay, now we're coming right along here. We got rid of that minus. If you don't follow it, just speak up. We'll explain it. Now here's something kind of weird. This ds. The ds is going this way. We're taking a test charge and we're going this way with it. But see, the dr is going this way to the right. R is a distance going to the right. So dr is a little distance going to the right. Here's the deal. ds is equal to a negative dr. They're button heads. They're going the opposite directions. We're going to the left with the ds, but dr goes to the right. So here, we're going to change this again. That'll make that a minus EDR. We're finding the change in voltage going from infinity to someplace, a distance from that point charge. And bam, 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 we're here. Okay, great. Well, I have an equation for electric field, and it goes like this. It goes K Q over R squared. You know what? That's a version of Coulomb's law, isn't it? Did I write big enough, Reagan?
Yes, sir.
You can read that. Hey, that's good. And we know how to integrate that. you can pull out the constants. There's a minus, there's a K, there's a Q. And what you have is integral of dr over r squared. Now we did something like that earlier. Remember it was the integral of dx over x squared? And you guys all studied that in calculus. And you know what it's equal to, don't you? It's equal to minus 1 over x. Remember that, calculus students?
Yes, sir.
Yeah, that's good. Okay, so what this is going to be, you know we're going to pick up another minus. So that minus and that minus goes bye-bye. And you have kq over r. And by Jove, I think that's what I wanted to show you. Look on page 303, and there's several other pages, but on page 303, they say the voltage is kq over r, right? And see, we're going from infinity to some distance r, so you would have to plug in infinity and r here. And but now wait a minute, auga. Somewhere I fell up. Yeah, there's two minuses there. There's a whole bunch of minuses going on. Now just a minute now. We're going from infinity to r. That r is our final destination, yeah. But what happened to the minus? Oh, well, I think I took care of that. It's a minus 1 over r, and so you get a minus 1. Yeah, that's it. And so what you wind up with is you'll get kq over r minus 0, because when you plug in infinity, you get a 0. And by Jove, we're done. Yay, we're done. We now have our equation for the voltage of a point charge, and we're going to work a problem now. Okay, great. This is problem 745. Let's do that. If you didn't understand that, I bet you did, but you could read it in your book. See, it's on page 303. Page 303. You could read that. It's right there. But you're going to need this equation Thursday night, so I would write it down. I'm not going to make you derive this whole thing. That would be cruel, wouldn't
Oh, yeah.
it? Okay, now we're going to do a problem. This is problem 745. And I told the people earlier, you get one sheet, 8.5 by 11, on one side, anything you want, equations. You'll want to put that equation on your sheet, but you need to know what it's good for. It's good for the voltage of a point charge. Okay, now let's look at 745. Let me find it here. I got lost again. Okay, here we go. 745, a 0.5 centimeter diameter plastic sphere used in a static electricity demonstration has a uniformly distributed 40 picocoulomb charge. Okay, let me draw that for you. So here's your sphere. we've got a sphere and it has 40 picocoulombs. 40 picocoulombs. You know what a pico is? It's back in the old days, years ago, they called them micro mics. It's a microcoulomb is what a pico is. What it amounts to is 40 times 10 to the minus 12 coulombs. Okay, so now this is a sphere. Here, let's put a little soap bubble. Artists kind of give it that three-dimensional look there. And we're going to put our positive charges on this sphere. Right? Let's see, I got lost. 45, where am I? Here I am. It's got a uniformly distributed 40 picocoulomb charge on the surface. What is the potential near the surface? Well, here, let me draw that. Here's your, they're asking for potential. Now remember, there's potential and there's potential energy. Potential is their word. How do you spell potential? There we go. It's their fancy word for voltage. Okay. And you got this electric field here. And we have the voltage. It's equal to K Q over R. Okay. And you know K, and Q is the 40 picocoulombs. What's the R? Let me read this. 0.5 centimeter diameter. Well, if it's 0.5 centimeters, that's 0.05 meters diameter. We don't want diameter. We want the radius. So that'd be 0.025. Okay, I'm going to shut up. You have 60 seconds. I know you can do this. Plug that in and tell me what the voltage is at the surface of that plastic sphere. Go for it. Well, I got a voltage. I wonder what you got.
14.384.
That's what I got. .384 volts. Right there. Good going. Now you could ask for voltages at other places if you wanted, like maybe I don't know. We could. I don't want to, but if we wanted to, we could. Now let's see how we did. That was 745. We'll see if we got that right. This says 745. They said 144 volts. Now wait a minute, something bad happened.
The radius is supposed to be 0.0025.
Oh.
Wait, I think we have a thank you point coming here. Yeah, the diameter, this is wrong. The diameter is 0.005 meters. So the radius is 0.0025 meters. And if you do that, you should get 143 answer book says 144 volts, I think. Isn't that what they just said there? 745. Yeah, I did it wrong, but I got it right. Thanks to my, here's a thank you point. Now, I'm not sure which student that was, but I thank you, and you know who you are. And so you got a thank you point. Good going. Excellent. Okay, well, let's do another one here. Any comments or questions? Okay, well, let's see if we can do this one. This is 779. I need some room though. Here, let me erase this. If you're happy, I'm going to erase this. See, I goofed up. Be careful of that. See, that would be 5 centimeters, but we didn't have 5 centimeters. We had 0.5 centimeters. So I goofed up. Okay, we'll make some room here. Now this is problem 779. Let's do that. Okay, let me find that. 779. Here we go. Electric field strength between two parallel conducting plates exceed the breakdown strength of dry air, which is 3 times 10 to the 6. Did you know that if you have air and the electric field is, well, that's dry air. I think if it's moist, humid air, it's a lot smaller. But if you have dry air and you have 3 times 10 to the 6 volts per meter, it'll arc. You've probably rubbed across a car seat maybe, or a couch or something, and touched a doorknob and have a little spark going on, the spark. Well, if you exceed an electric field of, you know what that is? That's 3 megavolts per meter, isn't it? If you got 3 megavolts per meter, the air ionizes. See, you've got oxygen, you have nitrogen, and some other things. The electrons, because of the electric field being strong enough, are ripped off of their atoms. You got a little lightning strike there. I bet you've had static electricity before. Now back to our problem. We're doing 779. If you have 2 parallel conducting plates and the air is breaking down, they're separated by 2 millimeters, potential difference of 5 kilovolts is applied. Okay. Let's draw the plates. Okay, here are these plates. And they are, how far apart is the question? They are 2 millimeters. They're 2 millimeters apart. Okay. That show up pretty good. Yeah, that's pretty good. They're 2 millimeters apart. And we're going to put 5 kilovolts. See, this one could be the 0 volts, and this one's going to be positive charge. This one can have negative charges. And this one is going to be 5 kilovolts. 5 kilovolts. So what? Well, we have constant electric field here. We're back to that constant electric field. And we need that student named Ed. Ed tells us that the voltage, if the electric field is constant, the voltage is just equal to ED. That's how you spell Ed. Okay? Well, now, if they give you the voltage and you know the distance, I know we can do this. You have 5 kilovolts. We're going to find the electric field that's constant. And the distance is let's see if I can get this right this time. It's 0.002 meters. All right, go ahead and solve that for me and tell me what you get for your electric field.
$2,500.
I'm getting 2.5. I'm getting an electric field of 2.5 megavolts per meter.
Oh, I see what I did. Yep.
Is it 2.5 times 10 to the 6?
Yes. 2.5 times 10 to the 6. Very good. We just found the electric field. Now let's see how we did. This was problem 779. Let me see what they said. 779. They said 2.5 times 10 to the 6 volts per meter. Now, you know what? That's smaller than 3 megavolts per meter. And so you don't get any lightning. Do you understand? The air is not ionized between those plates. Then in part B, how close together can the plates be? Let me read this again here. How close together can the plates be with this voltage? Okay, well, let's say you have 5 kilovolts. V equals ED. And let's say they're just close enough to where you ionize the air. So you have 5 kilovolts is equal to, I'm getting mixed up now. Yeah, we know what the electric field is. It's 2.5 megavolts per meter. And we're going to move them close enough together. No. I had a mental problem there. We're going to have it ionized, so you'll have 3 times 10 to the 6 volts per meter. And they want to know how close you can get them. This is as close as you can get them. Now, I want you to solve that and find out the distance that you can move those close together when you first get the lightning in there. Go for it. Solve for D. Well, I got a distance between the plates. Let me go to one of my outstanding students. Gee, I think we've lost a few. It's a long 3 hours. Let's see, I haven't picked on Phoebe for about a half an hour. Phoebe. What's the word? Unmasked? That's not right.
Unmute.
Unmute. There you go. Phoebe, unmute and tell what'd you get for the distance?
1.67 millimeters.
Yeah, that's what I got. Good for you.
Yay.
Yay, we did good. Now let's see what the answer book says. Here we go. I'm gonna look and see. It says here, what did we just do? 79.
How did you enter that?
And just a minute, I want to see if we got it right. 79 is 79. There we go. Now the answer book says 1.7 millimeters. Hey, they just rounded off. The book said 1.7 millimeters. I'm sorry, somebody said something. Anybody?
Oh, never mind. I got it.
You got it. You're okay. All right,
Yes,
great.
I'm good.
So if you move those a little closer together, see right now they're 2 millimeters apart. There's no lightning, but if you move them to 1.67, then there's going to be lightning. And what'll happen is you won't have positives and negatives anymore. They'll all be the same. Do you understand? The charges will equalize. It's all going to be neutral, if that makes sense. Okay, let's do another one. Before we do, though, let me tell you about charge rings. Let's do a charge ring. I'll show you the equation for a charge ring. Now, this is in your book. You could read your book. We've done charge rings before. What you do is you take a ring and then you charge it up. You put some pluses on there. There you go. And you come out here. And we're going to find the voltage. Now we know we have an equation for voltage of a point charge. If you have a point charge, we've got a lovely equation. I derived it. I don't know if you followed it, but it went K Q over R. And see, in this case, the R is right here. Here's you could call that a point charge. What's nice about this is that the R is the same for all the charges. See the R here? It's three-dimensional. Even in here, it's still the same distance. So for a that's the equation for a point charge. But now for the voltage for a ring of charge, it's going to equal to K times the total charge divided by this R. Now that R, let's call this the radius of your ring. How's that? That would be R squared plus X squared, square root of. See, here's X, here's R. This distance here is the square root of R squared plus X squared. And they have that equation, I bet, in your books in this chapter. Let me find it for you. Maybe you can find it for me. It's the voltage of a ring of charge. Boy, Jove. There it is. Electric field of a ring of charge. I found it. I got lucky. It's on page 323. Now they wrote theirs a little different. They went V equals K Q total over Z squared plus R squared. But see, what they did was they had their ring horizontal, and they had their distance Z coming up here, and they found the voltage there. So it's the same thing as what we got. We just had our ring oriented up and down, and they had their ring oriented horizontally, but it's the same thing, isn't it? You could read that how they did it on page 323. Now I want to show you something else that's kind of interesting. In this chapter, they show you there's a relationship between voltage and electric field. And it goes like this. The electric field is equal to the derivative of the voltage. Can you help me find that equation? Yeah, it's, well, they do it on page 320. Only they did it with respect to x. This is a dummy variable. It can be in any direction whatsoever. But it's a general principle. And if this is the equation here, we could take the derivative of that. Let's do the derivative of that with respect to x. Oh, that'd be fun. We have time. We'll work some more problems in a minute, but right now, this will be so much fun. We're going to take the derivative of this equation. Okay, well, we can do it. Let me write it so that it'll be easy for us. Now, this is the voltage of a ring of charge. And we're going to write it like this. Coulomb's constant, total charge on the ring, R squared, R is the radius of the ring, X squared to the minus 1/2. Can you get from here to here? Can you make it?
Yes, sir.
I know you can. And now we're going to take the derivative of it. Here we go. The derivative of it with respect to X should be, well, there's a constant there. That's supposed to say total, if you can read my writing. Now, when you take the derivative of this, you go minus 1/2 times that, minus 1/2 times that to the minus 3/2. You could put it in the denominator. But you're not done yet because you have to do the chain rule. You have to take the derivative of the stuff inside, which is 2x. And boy, you, I think we're done. Am I doing this right?
Is that
Wait, we
R
just
squared plus x squared to the 3/2?
Yeah. It's
Wait.
R squared plus x squared to the 3/2. See, you have to subtract 2/2 from a negative 1/2. And so what the 2's cancel, and it looks like what you wind up with is minus kq total over
When
R
we-
squared plus x squared to the 3/2. Now, there's something wrong with that, and that's that minus sign. I don't think it belongs there, because when we did this a long time ago, we solved this, and we got the electric field. Let me make some room here so you can see what I'm talking about. Go ahead,
when
anybody.
you
No, go
Go
ahead.
you're good.
Oh, I was just going to say that the 2x, should that be a negative 2x? That would take care of the problem.
Well, when you take the derivative of the stuff inside, you don't get a negative, you just get 2x.
When you take the derivative of the stuff on the inside, do we not need the like r squared too?
It's a constant. Derivative of a
Oh,
constant
okay.
is, but thank you for asking. And I think here's where my mistake is. I think I need a minus sign right here. See, if you put a minus sign right there, this becomes positive. And what you wind up with is the electric field of a ring of charge is KQ total divided by r squared plus x squared to the 3/2. And we did that. We derived that. It took us a whole big long board full of calculus. And it's on page 212. We used Coulomb's law, and we derived that. And there's that equation, only they got z because theirs going up and down and ours is sideways. So I think I need a minus here. Look in your chapter and find this equation for me and tell me if it has a minus sign on it. Because I'm a little bit rusty.
Yeah, it's on page 321, I think.
Yeah, there it is. You're right. It's on page 321, and it definitely has a minus sign. Look up at the very top. Now, I know
Oh,
that,
yeah.
well, look over on page 320 also. Page 320. Let me show you where that minus sign came from. But isn't that interesting that there's a relationship between the electric field of a charged ring and a voltage. See, there's a relationship between the electric field and the voltage of a charged ring, and there they are. And we just took the derivative, and boy, Jove, it worked great. But let me talk to you about that minus sign for just a minute. I need some room here. There's a little room right in here. It turns out that the change in voltage is equal to the negative of your E dot ds. Is that right? I think so. Let me see if I can find that for you. Yeah, there you go. Now, they don't call it S. For some reason, the book calls it L. And this equation's on page 305. And they're saying that the change in voltage in general is equal to the negative of this dot product of the electric field. Now, and they explain it on 305. Now, the reason for the minus, remember, comes from the fact that the change in potential energy is negative of the work done. And the work done is F dot, they use L for a dummy variable. Work is force times distance.
I'm sorry. Where does on the bottom there where we did the derivative?
Yeah, down here.
I understand how the 2 marked out. Where'd the x go there on the numerator?
Oh, when you take, tell me your name.
Jacob.
Jacob. We have to take the chain rule, Jacob.
Yes, sir.
And when you take the derivative of this, that's a constant, so you get 0. And the derivative of that is 2x.
Yes, sir.
You okay now?
Yes, that's where the 2x comes from.
Yes. And where the minus comes from is this fundamental equation that we talked about before, where the change in energy is the negative of the work done by the field. And of course, the work done by the field is QE dot DL.
I'm sorry, you might have misunderstood me, but from the 2x to the next step over though, like where does the x go?
Where does the X go?
Yeah, from that 2x to
Uh-huh.
the step on the right,
Yeah.
where'd the x go?
Where does the
How's
X
the
go?
x mark? Yes, sir.
It doesn't go. I think maybe I goofed up. It's Jacob I'm talking to, right?
Yes.
Jacob, you could wind up with a thank you point here, Jacob.
Well, Zach actually brought it to my attention, and then
That we could give that thank you point to both of you now. Just a minute. Let me think about this now. What we did was we took the derivative. I
Yes, sir.
erased some of it, doggone it. We had a ring, and we knew that for the ring, I think, well, this was to the, was that to the 1/2? My mind is
Yes, sir.
mush.
Yes, it was to the 1/2 because you have the 3/2 in the bottom over there.
There we go. But don't. Okay, now just a minute now. I'm thinking.
I think it was to the
It's a negative
1/2.
1/2. It's a
Yes.
negative 1/2. Uh-huh. Yeah. Okay. I don't think you need a denominator. I think that's it, isn't it? Divided by
Yes, sir.
yeah.
That's it. It was originally over the 1/2, and then you brought it up to the numerator, so that it's
Yeah.
negative.
So when I took the derivative of this, you get a negative 1/2. Wait a minute, I don't need two negatives, do I? Oh, because there's a negative here. That negative is from here, but then there's another negative from the negative 1/2.
Yes.
There's a 2x,
Yes, sir. From the chain.
and this is to the negative 3/2. So that gives you that to the 3/2.
Yes.
And then the 2's cancel, the negatives
Yes, sir.
cancel.
With the 1/2.
And I think, is it Jacob and Zach that I owe this to?
Yes, sir.
I think that needs to have an X there. And what about this? Well, that would have to have an X too, wouldn't it?
I believe so.
Look on page 212 and see if there's an X there. If there is, you guys are in with some lovely thank you points. Yeah, it's there. Now they have a Z, but that X has got to be there, and that's a big honking thank you point for Zach and Jacob. And I forgot to put it in there. You know, it's so nice to have students that stay awake during this. But it's correct now. And I think this is correct. And we had fun taking the derivative. We got time for another problem. So let's do one more. Okay, let's do problem 799. Okay, I need some room. Anybody else? That's really good. Anybody else? I guess not. Okay. We're going to do 799. So proud of you guys for staying with me to the bitter end. Let's see what kind of turnout we have here. Well, we got Zach, Phoebe, Jacob, and Nicholas. That's pretty good. And you're having your test Thursday night, and you're going to do good on that. Okay, this is $7.99. All right, here we go. $7.99. Let me find it here. Two parallel conducting plates, each of cross-sectional area 400 square centimeters. Well, let me draw those. We have two of these. And they're 2 centimeters apart. And each one has an area of 400 square centimeters. They're uncharged. We're going to put 10 to the 12 electrons. We're going to transfer from one plate to the other. Now, I need those in coulombs. 1 times 10 to the 12th electrons. And here's how you get the coulombs. 1.602 times 10 to the minus 19 coulombs is an electron. Why don't you put that on your 8.5 by 12 formula sheet that you're going to bring to class? Okay, let's do that, and we're gonna find the charge in coulombs that we're going to transfer. Okay, I could almost do that in my head. All right. See, the electrons are going to, they go bye-bye. See, the electron go bye-bye. And so what you wind up with is 1.602 times 10 to the, did I do that right? It's minus 7, isn't it? Yeah, coulombs. Okay, now that's going to make this one positive, and this one's going to be negative. And that they'll both have that same charge on it. It's just one's positive, one's negative. Now we need the area in square meters. So what you do is you take 400 square centimeters and you multiply by a meter is 100 centimeters and square it. That'll get rid of the square centimeters. Help me do that. $400 divided by 100 squared. Did you get 0.04 square meters? Okay, we got the area. Now, I think what we want, they want the potential difference between the plates. Okay, we'll get that for them. I think what we want, there's this lovely equation that goes like this, that we know and love. I think we derived it with Coulomb's law. I don't know if I ever did it with Gauss's law. Man, if we only had enough time. We could derive that in Gauss's law in 3 quick and easy steps. They do it in your book. Read your book. But see, we can get the electric field between here. We can get it. It's going to be 1.602 times 10 to the minus 7 coulombs divided by 0.04 square meters. Okay, do that for me. Oh, wait a minute. Don't forget the epsilon 0. Okay, now do that for me and we'll get the electric field between the plates. Go for it. Well, I've got the electric field, but we're going to call on one of my wonderful students. One of my wonderful students that is so stubborn, they have not given up. They're still with me. Nicholas, what'd you get?
I haven't got anything. Still trying to figure out where.
Take your time. Plug that in and find the electric field for me, Nicholas.
I have like some 452,000 number.
That's what
No,
I
Nick-
got. That's what
Really?
I got. 452.
452,337.9264.
How about that?
Yeah, that's
452 kilonewtons per coulomb. Or you could go kilovolts per meter. The same thing.
On the exam, would you prefer us to?
Doesn't matter. They're equal.
Okay.
Now, that's not what they wanted, though. They wanted the voltage between the plates. And they use their own fancy language. See, they want the potential difference. What that is the voltage. When they say potential, they mean voltage. Okay, well, we're going to get the voltage. Here's where I need my student. See, there's some room right there. I can do that. Now, here's how it works. V equals ED. Now we have the E. Ta-da, and it's 452.3 kilonewtons per coulomb. We have the D. It's 2 centimeters. All right, I want you to take those two and multiply them and get the voltage between these plates. On your mark, get set, go. Well, let's see. How about my friend Zach? Zach, unmute and tell me what you got for the voltage between these plates.
90,460.
You might be right. I might be wrong. I'm getting the same number, Zach, but I'm getting 9,046 volts, and you got 90,460. Do it again.
Wait, which equation do we do? I think I did the wrong one.
Well, we got the E. The E is sitting right here. There's your E. And the D, but you're going to have to write that as 0.02.
Oh my gosh, I did do the wrong. Thank you.
Got 90/50, but that's close enough, I guess.
That's close enough for me. I'm happy. I think we just had a round off thing going on there, but we're both happy, I think. And what about my friend Zach? Are you okay now?
Yeah.
Good. And now they wanted something else. What is the potential difference between the positive plate and a 1.25 centimeters from it? Okay, well, let me see if I can find that. See, if that's 2 centimeters, that'd be 1 centimeter, and they wanted 1.25. That'd be kind of right about in here someplace. Well, it's just a matter of going, well, let me see, I'm getting confused now. the difference in voltage going from here to there, or you could go from here to there. I think I'd rather go from here to here, guys. Because see, this is 0 volts here, right? And so 1.25, isn't that distance 0.75 centimeters? I think it's 0.75 centimeters. See, if this distance here is 1.25 centimeters, that's 0.75, isn't it? Yeah, I think so. Okay, so I think what you got here is 452.3, we'll write it like this, kilovolts per meter. There you go. And multiplied by 0.7, wait a minute. Aren't you going to have to move it over, would it be 0.0075 meters? Did I do that right? I think so. That should give you the voltage at that location. Do it. Multiply that and see what you get. Better hurry, we're running out of time.
I got 3,392.
That's what I'm getting. I'm getting 3,392. Well, what would be the units? Hey guys, if you're solving for voltage, what's the units for voltage?
Volts.
It's volts. All right, let's look at the answer book and see what they said. This was problem 799. And they said, minus 5.7 times 10 to the third. You know what they're talking about? They're talking about the change in voltage from here to here. And I think they're right. But the change in voltage from here to here is this here. They add up to the total, which is, what was the total? Well, it'd be 9,000. See, if you add these up, you get 9,000. It all depends on how they ask the problem. How did they ask it? Let me read it. What's the potential difference between the, oh. See what I gave them? I gave them the potential difference between the 0 plate and the location. They wanted the potential difference between the positive plate and the location. And it's negative because you lose. This is positive because you go up. Did I confuse anybody? I hope not. It kind of depends on what they're asking for.
Where'd you get the 0.75 from? Is that just the given value? Or?
I tell you what, if you have 2 centimeters, and I broke it into 1.25 and 0.75.
Okay.
That's what I did. And what I solved for was the change in voltage over here, and what they wanted was a change in voltage here. I think we did it okay. I didn't answer what they asked for. Well, it's been fun. I'm so glad we had this time together. Like Carol Burnett says, here's your last chance to say anything. I'm going to push this little red exit button here. Here's your chance.
Is there like a certain way you would decide that offset on how you split the 2 centimeters?
They asked for 1.25. They gave us the 1.25.
Oh, okay. It's
Yeah, it's in the problem. It was in this 799. Anybody else? We're going to go bye-bye. I'll see you guys Thursday night. Take care of yourselves.
See you
All right.
Thursday.
Bye.
Bye-bye.
Bye-bye.
Thank you.
Thank you.